my back was turned that my battery was, or my memory was full. I think I've been keeping it clean. We'll see what happens. So I can see it again here. I don't know if you can see. You can't see it, but hopefully we can get the recording for most of this. All right. So the product should have less energy than the reactants. All right. So if we thought about that. Here's a spontaneous reaction. So we haven't sent a space shuttle up in I don't know how many years now, but you've probably seen pictures. All right. The reaction that happens out of those fuel tanks in the big tank that was on the space shuttle, what it had was, we could think about this as, this reaction is really only go one direction. But what you could think about that is we have this going on. So I've got two hydrogens molecules react with one oxygen molecule to make two water molecules. That's a very spontaneous reaction. It gives off a lot of energy. You know that because you see flames coming out of the back of the space shuttle, right? That's a lot of energy being released. And so this is spontaneous. Okay, and what it means is it gives off energy. And what it means is that the water is more stable. It contains less energy than, two waters contains less energy than two hydrogen molecules and two diatomic oxygen, or one diatomic oxygen molecule. Questions? Okay. But how much energy? And that's where this bond energy comes in. Okay. We can use that table. We can use the bond energies to calculate how much energy would be given off in this reaction. So, to do that, what we would do is we would draw the Lewis dot structures for everything, and we would see how many of each bond we have. Okay, here we have a good use of Lewis dot structures, right? We had to learn Lewis dot structures. They tell us about things. They also tell us about molecular shape that we'll do after this today. But if I look at this, I have two hydrogens, okay? And this would be our correct Lewis dot structures for hydrogen. All right, if you go through your Lewis dot protocol, you will get that your best, and best is most stable, structure for oxygen looks like that, diatomic oxygen looks like that. And then after that, we're going to make two water molecules, right? This would be your best Lewis dot structure for water. And if I draw it out like that, now I know exactly how much of each kind of bond I need. And if I subtract the amount of energy needed to break all these bonds, or I take the amount of energy needed to break all these bonds and I subtract the amount of energy needed to break all these bonds, that will give me the energy of reaction. Okay, so I'm going to do products minus reactants. And in chemistry, it will almost always be products minus reactants, unless it's products divided by reactants. Occasionally there are exceptions. But if you don't remember, and you can tell from the context of the problem whether it's products divided by reactants, right, or products minus reactants, it's one of those two. It's not the other way. Okay? You can't remember. That's the guess you want to make. Let's say, you're taking your MCAT in however many years. 3 years you're taking your MCAT and you're trying to remember, and chemistry, Gen Chem was a long ways away, right? Products minus reactants, products divided by reactants. It's probably not the other way. Okay, so let's go ahead and do this. What kind of bond do I have here? It's a single bond, right? And it's between an O and an H. How many OH bonds do I have in the products? 4 OH bonds, right? 2 for each water. So 4 times OH bonds. All right, and so that what I can do is let's go up to our table and look up what an OH bond has. An OH bond is worth 460 kilojoules per mole. Okay? So this is going to be 460 kilojoules per mole times 4. Let me, or let's just put an arrow there and just say 460 kilojoules per mole. Because we're about to write this out in an equation. All right. So you guys have probably written this down in your notes, right? What I want you to do is, so we do products minus reactants equals energy produced or absorbed. And let me go ahead, products, bond, energy of the reactants or the products, whichever one we're doing there. Okay? So what I've got is I have 4 OH bonds, right? And that's my products, right? 4 OH bonds right there on the product side for the reactants. So I'm going to subtract from that. I can subtract, it's 2 HH bonds, 2 times HH, right? Okay, and I also have to subtract my oxygens, 1 times O double bond O. And that's going to give me my energy produced or absorbed. You guys all with me? Has everybody written what I just wrote down for that equation? All right, well, I want you to go up here. Go ahead and solve that. And meanwhile, I'll look and make sure it's all on screen. Yeah, okay, good. Call me over if you have a question. Anybody need more time? All right, let's go ahead down here and solve this. So what did you get for, what was the energy of an OH bond? I'm going to do these dots for multiplying. 460. Okay, and that's kilojoules per mole. What's the HH energy? 436. Okay. And what's the oxygen energy? 498. And what did you guys get overall then?
476.
476? Is it a negative 476? It's not?
Wait, yeah, that's my
470. Yeah,
You got what?
I got 470.
470, is it negative?
Yeah.
No?
No.
It's got to be negative.
And 460 times 4 is not a lot.
It is.
And we only have.
Did I make a mistake in terms of something I was supposed to put in here? That was all the bonds, right?
Yeah, I got 476.
Yeah. I'm going to do this, but I trust you guys. Well, all is not right with the world.
Oh, it's 470.
Okay, well, I get 472. So that's 470 kilojoules per mole. Okay, well, that's how you would solve that problem. Okay, I'm surprised it's not negative. I will get back to you on it. But in general, in chemistry, what we do is if it's a negative sign out here, it means energy's given off. And I know this reaction gives off energy. So I'm a little confused, but I'll figure it out and get back to you on that on Monday. Okay? So look to solving those problems in that way. Okay, so, but this is actually a really useful tool because it allows us to figure out energies of reactions. All right, any questions? All right, then we're going to talk about molecular shapes. Okay, and what I'll tell you is so the bond energy things, yeah, that might be on the test, might have a brief problem on that test, but really what's really important, we've learned Lewis dot structures now, right? We've learned formal charges, learned ways to figure out the good Lewis dot structures, and we're going to use those Lewis dot structures to determine molecular shapes, and that's super, super important for what we're doing. So those are going to be big items on the test. So let's talk about molecular shapes then. So what happens, there's a basic rule here. We're going to use a theory that's called DESPER. Okay, and what that means is valence, shell, electron, repulsion theory. I don't know how that fits, but we call it DESPER. And it's essentially about how, when you draw a molecule, how many electrons are around the center atom. So the way it works is you're going to use how many electrons are around the center atom to determine shape. Okay, and what you're going to do is you're going to pair those electrons up. Pair the electrons up. Okay, and in doing that, a bond is 2 electrons. Well, bonds go together. Okay, so I'm going to say a bond is 2 electrons, but a double bond is 1 unit. A triple bond is 1 unit. So single, double, and triple bonds all count as 1 unit. Okay, pairs of electrons count as a unit. So 1 single pair. I'm going to say single pairs of electrons. So 1 pair, not if I have a bunch of pairs, I group them up. Single pairs of electrons count as a unit. Okay, so we have a pair, we have bonds, and we have pairs of electrons. All right, and then the rule we're going to use is that groups of electrons are going to move as far as possible away from each other on that center atom. So imagine that center atom as a sphere. How can I arrange everything around on that sphere so it's all as far away from each other as possible? All right, remember, electrons are negative, they're repulsive, and they're going to push away from each other. Okay? So the process you're going to use here is the process to determine shape. What you're going to do is draw a Lewis dot structure. Draw the best Lewis dot structure. Once again, best is most stable. And then you're going to use the structure to determine the shape. And that's based on how many groups of electrons are around the center atom, or on the center atom. Okay. So let's start doing this. And we're going to work through a whole bunch of different shapes here. So let's say I'm drawing carbon dioxide. And what I'm going to do is I'm going to kind of fly through a Lewis dot structures. I may have you do some examples where I have you tell me what shape things are. But I'm going to assume you've got your Lewis dot structures down. If you don't, you'll want to practice them more. They will be on the test, and they will be a big deal on the test. Carbon dioxide. Okay? Center atom. How many groups of electrons on that center atom? There are 4 bonds, but remember I group my bonds together, so double bonds count as a unit, right? 2, right. 2 groups of electrons. If I have 2 things, if my head's the center atom, how can I put those 2 groups of electrons such that they're as far away from each other as possible? Yeah, opposite each other, one on one side, one on the other, right? Okay. So what shape would that be? They'd be in a line, right? That's how I get them as far away from each other as possible. And so in chemistry, we call that linear. Make sense? Why it's that shape? What the shape is? All right, let's go ahead. Let's do another one. How about formaldehyde? And now I'm going to start drawing things as best I can in 2 dimensions, in the actual shapes they are. I may have not been so careful about it before. So now I have, that's the Lewis dot structure for formaldehyde. What? How many groups of electrons do I have around the center atom? 3, right? So now I can't do this with my head so well, right? Imagine my body or my neck is one of those groups. How do I put these other 2 groups that they're as far away from each other as possible? I would do this, right? So I'd have a triangle, okay? We call that trigonal planar. We haven't really started using 3-dimensional space yet. All right, let's try water. I'm going to try to fool you with water. Okay, water. How many groups on that center atom? 4, right? 1, 2, 3, 4. The electron pairs count as groups. We haven't had that happen yet before. All right, so I've got 4 things around that center atom, 4 electron groups. And so what shape do you think that would be? Purposefully tricking you here. Kind of looks like a square, right? It's not a square because we're in 3 dimensions. All right, so let me show you. So if you go to 4 dimensions and you want to break these things up so we can see them, let's see if this wrecks my recording. It hasn't. It looks like this. Okay, so this has 4 atoms, but imagine this is a water, right? What I'd have in 4 dimensions, this is a tetrahedron, so we call this tetrahedral. Okay, you can see with the little triangle there. You can also see the shapes here. Imagine that's a pair of electrons, that's a pair of electrons, and if we just look at the atoms, we end up with this bent shape, right? Okay, so the global shape is tetrahedral, but we only name the atom shape. So the atom shape, so if I was to draw this, it would look more like I'd have a pair of electrons up here, I'd have a pair of electrons back there, right? Okay, in space, and then I'd have an H there and an H there. All right, and so this is bent. And let's go ahead and do our basic shape, though. The base shape it comes from is tetrahedral. If you arrange 4 things in space as far away from each other as possible, that's a tetrahedron. So what we can do is we can get our tetrahedral we get with methane like we just saw. This is tetrahedral. Let me write it out as one word. Like that. Okay, does that make sense? So we have tetrahedral, okay? And then if we put something on one side, we have a version of bent, right? And you guys see, remember that there's 4 electrons here. These are just closer than those 2. Okay, they're coming out of the board and the other 2 are going back. The way we actually draw that when chemists try to draw things coming out of the board is we do these wedges. And then we do little dashed lines showing things go back. Okay, like that. Questions? Okay, I think if we do SO2, so this is well, let's do NO2. I'm trying to remember how NO2 ended up. We've done NO2 before. Let's do NO2 and just see what shape we get. So it's NO2 minus, right? I'm going to actually have to do this one. Like I don't have it memorized. So 6 and 6 and 5 and 1 extra electron, right? For the charge. So we've got 18 electrons to play with. So what I want to do, what I'm hoping I can end up with is something like this for my example. Formal charge 0, formal charge 0, and then, did I use 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, I did it. Okay? This one's interesting, right? So we'd have formal charge to be over here, it'd be negative. How many things do I have around the how many electron groups do I have around that center atom? 3. So 3 gives me trigonal planar, right? Okay, but when I draw that trigonal plane, that I've got one of those spaces is taken up by the electrons, right? So what the shape of the atoms looks like here, if I was to draw this in its shape, I'd have my pair of electrons on one point of the triangle. I'd have an oxygen down here at the other point of the triangle. And I'd have another oxygen down here at the other point of the triangle. And do you see that's another version of bent? But it's a version of bent where we have two pairs of electrons up here as opposed to one pair of electrons. And so the angles on the shapes are going to be different. We'll maybe go back and rename the angles on the shapes, but I want to make sure I get through all of our shapes here. All right, so we've got tetrahedral, bent. We could also draw another tetrahedral molecule. Looks like this. This is ammonia. We've seen ammonia before. Ammonia looks like that, right? How many things around that? How many electron groups around that? 4. So the base shape is tetrahedral, except they're not all atoms, so we're going to have another name for it. Let's go ahead and go back, and I think there's an example on that page I was on. Let's see, we're looking for, there it is, ammonia. You see what ammonia looks like here? Tell me, why do these hydrogens go down? Why aren't they just straight out? Yeah, because there's electrons right here. There are 2 electrons right here pushing them down. What's that sort of look like? Trigonal, it kind of looks like a trigonal pyramid. It looks like a flat squashed down pyramid. So we call those trigonal pyramidal. Trigonal pyramidal. Okay, for this one. So what I want to do is back out here in terms of magnification. And I want to get all of these on the screen at once. Okay, and I want to point out once again that all of these, if I take water, and I take trigonal pyramidal, and I take tetrahedral, these are all subsets of tetrahedral. Okay, they're all tetrahedral, but we only name the shapes of the atoms. So as we replace atoms with electrons, we get different shapes. Does that make sense? You see how we're getting the shapes? It's just things moving as far away from each other in space as possible. All right, so that was 4 things. Let's build up to more than 4 things around a center atom. Let me go ahead and zoom us back out again. All right, and let's go ahead and look at what might our next shape be. Phosphorus pentachloride, so PF5, that's interesting. What do we get there? Do you see this shape here? This is going to be called trigonal bipyramidal. Do you see how it's like a pyramid on top and a pyramid on the bottom? Okay, that's when we have 5 things around a center atom. So let's go ahead And just quick draw the Lewis dot structure over here. So if I take a phosphorus and it was chloride, right? So I'm going to go ahead. Was it fluoride? Okay. So we could make it fluoride instead or fluorine instead. And then, but this is going to be, you can double check by drawing a Lewis dot structure if you want. This would be the Lewis dot structure you would draw, okay? Forgive my fluorine over there. But, so this is 5 things around. If we spread all 5 things of those around the center atom, and we try and spread them out as far as possible from each other, you end up with this triangle with something popping up above and below. And like I said, we call that trigonal bipyramidal. Okay, questions? Does that make sense? Why that's what it is? Okay, let's go back to the shapes. What else have we got? We've got PF6. I don't want to do that one just yet. I want to do sulfur tetrafluoride instead. Well, this is interesting. What's going on here? What does this look like to you? Trigonal bipyramidal, but with a pair of electrons right here. Okay, and that's what's going on. We'll draw the Lewis dot structure in a second. So if we look right here, what this is what? This is sulfur tetrafluoride for when we talk about it in a minute. This went here. So why did this go here? Okay, when we think about space, I haven't talked about this yet, but those lone pairs of electrons, they take up lots of space. They take up more space than the bonds do. Okay, we talk about groups of electrons, and do you see if we look at the angles here, if we look at a triangle, what are the angles between the points of a triangle? Like right here. What's that angle? It's 120 degrees, okay? 120, 120, 120. But going straight up above the plane is 90 degrees, okay? So if I put my lone pair here, it bumps into things less than if I put it up here. But if I put it up here, it's going to bump into 1. It's got 90-degree angles with 1, 2, 3 things. Whereas if I put it here, it has 90-degree angles with 1, 2 things, if that makes sense. Okay? So there's more space, essentially. So let's go ahead and go back. All right, and so what sulfur, what that tells me is, you know, if I didn't have it exactly in my head, what these were, and I kind of probably didn't. If you told me sulfur tetrafluoride, I'd have to think about it a minute. But now that I've seen the shape, that tells me that this is going to be the shape. This is going to be the Lewis dot structure for that, okay? And it's a subset of trigonal bipyramidal. We call this seesaw. I did not make these names up, okay? They're just what the names are. Okay, because it's kind of like a seesaw. If we turned it on its side, you could go back and forth, right? Stood it up on these 2 fluorines. Questions? All right, let's do our last couple shapes then. But remember, I'm showing you shapes with their Lewis dot structures. And here at the end, I've switched to showing you the shape and then showing you the Lewis dot structure. What we would do is we would make the Lewis dot structure, right? And then we'd use that to determine what the shape is based on how do I spread things out most. And there'll be a table in your book that will talk about what shape goes with how many lone pairs of electrons and how many atoms attached, okay? When we talk about atoms attached, that's a bond group. But really, how it works is it's about spread. It's not this magic table. It's how do you spread things out as much as possible. Okay, I'm almost out of time. I'm going to show you two more shapes, and then we're going to work on this more on Monday. For the homework I give you, you might have to either read to get them or just skip past them. It'll be, as long as it's a homework that you can do as much as you want to get full credit. I might have to give you some that we didn't cover as much as I would like so far. But let's go ahead and let's look at two more shapes. So we've got one final set of shapes here. Phosphorus hexafluoride, or this is okay, this is called hexafluoride. I'm going to call it phosphorus hexafluoride is how we would name it. Look at this. This is an octahedron. Okay? So we call this octahedral. But 6 is as high as we're going to go, putting 6 things around, or 6 atoms around the center atom, or 6 things. So this is going to be octahedral. Okay? If I replace one of these, do you see I have a square pyramid? Let's go ahead and look at that shape real quick before you leave the room. Let's see. I don't see that I have a square pyramid shape here. I will have to introduce you to a square pyramid on Monday. Okay? All right, you guys have a great weekend. Look for that homework.